Welcome to qnawire.
Number one, the table shows the year and population in millions of Texas. We want to use an exponential model. So let's first get the data into a calculator using Desmos. So we've got the year 1900 with 3.1, 1920, 4.6, 1940, 6.4, 1960, 9.5, 1980, 14.2. We want an exponential model on this, which looks like y1 is approximately, because we're using decimals, we use x1, y1, is approximately a times b to the x1. We should have it in log mode as well. All right, so a model for this, which we might be better off if we did this as 0, 20, 40, 60, and 80, representing years since 1900. It'd be, yeah, better to write a function with. So we have y equals 3.095 times 1.019 to the x, where x is years since 1900. So for the year 2020, we would substitute 120 for x, or we could just, yeah, we'll do. So 3.095 times 1.019 to the 120th would be 29.6 million. The table to the left shows the closing prices for NASDAQ stock index at the end of February during certain years. Use an exponential model and then estimate the year the closing price will reach 10,000. All right, so again, if you want, you can arbitrarily create, you want x's in years since, well, we could say 92, or we can say just 1990 to make it easier. It's whatever you want to define it as. So if I say 1990, then it would be 2, 633, 4, 793, 6, 1100, 8, 1771, and 10, 4696. Again, x is years since 1990. An exponential model, y1 is approximately a times b to the x1. Log mode for Desmos, and we can say 320.276 times 1.272 to the x. And when will it reach 10,000? In this instance, I think what I'll do, instead of solving, I'll use the technology and just say, when is y going to be 10,000? And we can interpret this as 14.3, which would be 14.3 years from 1990, which would put us in the year 2004. A logarithmic model for the next function. Again, I'm going to enter the table of data. Let's say we're going to go x years since 1970. And so we'll say 0, 30, 1035.3, 1537.9, 2037.2, and 2006 is 36 years from 1970, and that's 41.5. All right, so a logarithmic model would be y1 is approximately, we could do a plus b times the log of x. I bet this is having a problem with 0. We can say cx plus d, and I bet that will, if we give it more options. Okay, so there we go. This is a version. And so one way to model it with a logarithm is 26.024 plus 15.1 times the log of 0.23x plus 1.84. Okay, and then if we use that to determine or estimate the percent of female workers in 2016, that would be in 10 more years, or since 1970, that would be 46. And so we can say, when is x equal to 46? And that is 42.6. And that would be the percent of the population. Last one, we don't need to adjust x value, so that's convenient. So I'll add my table, 1, 2, 3, 4, 5. So it's 1, 4, 2, 6.33, 7.94, 9.2, and 5, 10.3. We want a logarithmic model. I'll start with to see if we can do a simple 1a plus b log x. That does work out for us. We can say it's 3.818 plus 8.95 times the log of x. And then we can use it to determine the age of the tree at 20 feet. So that would be when y equals 20. And we'd estimate the age to be about 64.3 years old.